Welcome to this special edition of Frequency Matters, the RF and Microwave Update Series. I'm Pat Hindle, and I'm here with my co-host Gary LaRude and special guest David Cruickshank, author of a new book being released by Artech House Publications called Implementing Full Duplexing for 5G. Welcome, David.
Thank you.
David is a microwave materials applications consultant with more than 40 years of R&D experience, applications engineering, engineering management, and general management at Ferrante Radar and Raycal Electronics in the UK, and also Skyworks Transtech in the US. He's going to release a new book at the end of the month from Artech House Publications. So David, full duplex has been a goal for many years, but we've never really achieved it on full-scale commercial level. What are the technical issues that still remain before this is realized?
Well, of course, the big advantage of full duplexing is you get twice the capacity for the same spectrum. The cost of new spectrum, as we all know, is pretty high. And the suitability of new available frequencies is also questionable in terms of coverage and capacity. So full duplexing has a role to play in future cellular infrastructure. In the book, we don't talk much about multiple access because I believe the problems are largely centered on the physical layer, which is essentially the transceiver in any of the platforms. So if we look at the full duplexing transceiver, we're in a situation where we have a very relatively strong transmitted signal and a weak received signal. So we have to achieve something in excess of 100 dBs of self-interference cancellation because the transmitter and receiver are at the same frequency. So if we look at that in the transceiver, that is essentially the sum of the what's called the passive RF isolation at the antenna or near the antenna, active cancellation at the first RF stage of the transceiver, and then finally digital cancellation during the A to D conversion process. In rough terms, that problem is easier with relays, a little bit more difficult with access points, more difficult with base stations, and extremely difficult with mobile units because of their small size and complexity. So the first half of the book is about the transceiver architecture, whether or not you need an auxiliary transmitter or receiver, whether you can use an architecture that misses out the first RF step and goes directly to the mixer, which is called the mixer first approach, and looking at the pros and cons of each architecture. However, when we do that, we soon realize that most of the problems are centered around the passive isolation at or near the antenna. And the kinds of solutions that have been put forward are really three. One is to use two antennas, which of course takes up more space, and you have to separate them physically to get the isolation, so that takes up even more space. Cross-polar isolation, where you can use two senses of polarization, the transmitter in one sense, the receiver on the other. But there are some issues with that because of reflections and so on, changing the polarization of the reflected signals. So the third solution was generally thought to be the most elegant, which is to use some kind of duplexing circulator.
So from your experience, what techniques for reducing self-interference work best?
Well, in the book, we survey the kinds of techniques used by the various university groups who've been involved in this kind of research. The most successful people have been a group in Stanford University and another one in Finland, Tampere University. And both of these groups achieved significantly greater than 100 dBs of self-interference cancellation by addressing both the linear and the nonlinear parts of the cancellation process. And it's kind of a time-consuming discussion to get into the weeds of that, but essentially that was part of the success. And the other one is when you're dealing with MIMO, where you have a number of adjacent transceivers, the problem becomes crosstalk between each individual transceiver and its neighbor. And again, both the Stanford and Tampere approaches successfully dealt with both the linear and nonlinear aspects of the crosstalk. And then there's a third issue which relates to antenna positioning in MIMO, because there are constraints on what you can do in terms of spacing of antennas. So the bottom line is that a combination of these considerations led both Stanford and Tampere to individual cancellation techniques. They're quite different from each other. And so the book addresses the pros and cons of the two successful approaches. The disadvantage of both their techniques was that in order to test out the transceiver, they either had to use a large, expensive circulator or two antennas. So they weren't able to get around the duplexing circulator problem themselves. They simply just used a commercial large circulator or two antennas. So the problem kind of narrows down to getting to a small, cheap, easily integrated duplexing circulator.
So what are some of the latest advances in circulator technology, and how are they being applied to full duplex technology?
As we said, the conventional ferrite circulator is too large and expensive. The other technique that's been put forward is called the electrical balance duplexer. But because it is essentially a hybrid circuit, it inevitably has an irreducible 3 dBs of loss in one direction. And neither of these solutions really is adequate in themselves. So a new technique that's come up in the last few years is completely different. It's from the physics community, and it's called spatio-temporal modulation. And essentially, it simulates the properties of ferrites by switching either resonators or transmission lines in such a way that you can create differential phase between the two switch states. And that's really the secret of a junction circulator. We have differential phase between the circulation in one direction and the circulation in another direction, the clockwise and anti-clockwise directions in a circulator. So the principle of STM was established just a few years ago. The problem with the early STM was that they were unable to simulate the 120 degrees phase separation you need. They were forced to use combinations of 90 degrees and 180 degrees. And that creates an intrinsic asymmetry in the distribution of the energy around the ports. And the effect was that the S parameters, that is the insertion loss, return loss, and isolation, were relatively poor compared with the ferrite circulator. But the promise was there in the technique.
So I am relatively familiar with ferrite circulators, but not really with semiconductor circulators. Can you talk about that technology and compare the two?
Yes, the comparison is really most relevant when we're talking about the frequency that we want to use these devices at. So if we look at below 1 gigahertz, where ferrite devices are extremely large, unless you use a kinesis structure, which has poor insertion loss and bandwidth, you're looking at a very large, expensive item. With STM, if it's realized in LC circuits as the resonator or the resonant length, we can make the device significantly smaller than a ferrite device. Furthermore, if you can incorporate it into a CMOS circuit, it can be made even smaller. So STM is promising in that direction. And one new development which has come up in the last year actually is something called differential STM, where you take two STM circulators, configure them in a back-to-back arrangement, And that has the effect of curing the symmetry problem. And in so doing, also the linearity of the STM device. So below 1 gigahertz, I think that the STM approach using LC potentially integrated into CMOS is the answer relative to ferrites. Between 1 and 3 gigahertz, though, we have problems with LC to do with Q and so on. And yet another relatively new approach in the last couple of years has been the suggestion of using either ball or saw resonators rather than an LC resonator. These have higher Q than the corresponding LC component. Not so easily integrated, but nevertheless, combinations of lower loss switches and ball or saw open up the possibility of using STM in the 1 to 3 gigahertz region. Now, you might argue, well, isn't ball going to go to 5 or 6 gigahertz? But it can do that, but the Qs get poorer and poorer as you go higher in frequency. And I doubt if it will be able to get to the level we need to get to for STM based circulators, although it may be perfectly good as a filter. So above 3 gigahertz, the answer would appear to be if we could make the ferrite a bit smaller and cheaper and easier to integrate, that might be the best solution. And that's what I'm suggesting. So to summarize your question, below 1 gigahertz LC STM, between 1 and 3 ball or saw-based STM, and then above 3 gigahertz, a better ferrite device might be the answer.
What are the new developments in the area of materials and packaging?
Okay, well, another new development in the last few years has been the development of high dielectric constant ferrite materials. And in combination with higher dielectric constant dielectrics, especially in the 3 to 6 gigahertz region, where size is a particular problem, we've been able to reduce the footprint of ferrite devices by greater than 1/2 of the original value. So we can make them pretty small just by shrinking them dielectrically, if you like. The other thing is most circulators right now are in strip line. If we move to microstrip, that has a lower profile because you only have one magnet and one ferrite disc. It has a smaller parts count, so is therefore cheaper. It's more easily surface mountable and therefore more easily integrated into a multi-function module, for example, of the type you might want to use in a small form factor base station or conceivably even mobile unit device. That's one aspect of the above 3 gigahertz situation that we can improve. In the SAW area, there are now available piezo devices based on single crystal acoustic resonators, which have got higher Q than conventional ball or SAW, and therefore lower loss. And so in combination with lower loss switching, which you can do by improving either the semiconductor switch or going to a MEM switch, we might expect to see an improvement in the insertion loss of the 1 to 3 gigahertz SAW or ball based STM device. Another approach talking about much higher frequencies in the millimetric region is the use of substrate integrated waveguide, where you can use higher dielectric constant ceramic instead of laminate, and therefore make smaller devices. We tend to forget that we might need a filter in some of these transceivers. So SIW has been shown to be better in ceramic. And also we can conceive of an SIW circulator, which is going to be smaller than a conventional ferrite. It's something of a problem that at millimetric frequencies, conventional ferrite is actually pretty small. Its size is not the problem. It's more of insertion loss. And so SIW gives better insertion loss typically than microstrip does at millimetric frequencies. So again, it's a combination of these types of factors that would give us better full duplexing transceivers in terms of materials and packaging.
So as you look at this landscape, what technologies or developments are actually nearing the market that will enable full duplex systems?
Well, the answer is it's a series of different things. I don't think there's any one thing that is going to do it in itself. The key, obviously, is integration and achieving small size and low cost. And so if we look at CMOS, for example, we know that CMOS is going down in nanometer scale terms, which means that its higher frequency performance is improved. And so we might expect to see higher frequency CMOS, certainly comparable potentially with gallium arsenide or gallium nitride. So better CMOS in that respect. The other thing that's going on with CMOS is more layers, more metal layers, and better dielectric loss in the insulator layers, which would result in better Q devices in terms of LC circuits, and the ability to get to higher values of inductors or capacitors, inductance or capacitance in the same volume of CMOS. And then, as I mentioned, there's MEMS will give you better Q and better insertion loss than, dare I say, semiconductor switching or tuning devices. MEMS has a cost problem relative to semiconductors, but we might expect to see the gap between the two technologies and cost narrow a bit in the near future. The other thing that's coming along is silicon on insulator technology. Quite recently, a company has introduced piezo devices into their silicon on insulator portfolio. And that would obviously allow you to combine active devices with piezo devices of the type you might need for SAW or ball-based 1 to 3 gigahertz SDM circulators. If we're talking about longer term, because I think you said short term, longer term, there are other things out there. For example, self-biased ferromagnetic nanowires, which can be embedded in insulators like silicon carbide. And of course, silicon carbide is used these days for gallium nitride amplifiers. So the combination of potentially duplexing ferromagnetic nanowire circulator with active gallium nitride devices offers another integration possibility. Whether it's cheap or not, we don't know yet. And then if we look at the organization of the platform itself, there is a movement away from purely planar structures towards layered structures. And we might expect to see, for example, a top layer of the antenna and the near antenna passive components, and then a layer of CMOS, let's say, or improved CMOS for the transceiver. And then below that, we might then see a CMOS-based digital signal processing for both the beamforming that we know we need for MIMO longer term, and also the DSP for the self-interference cancellation. So we might expect to see integration of the DSP itself between beamforming and SIC, and then potentially beyond that, RF and DSP integration, all in CMOS. Okay, so I think that kind of sums up a number of possibilities in the near future.
Well, Dave, thank you for talking with us about the state of full duplex technology. It's all very interesting. And for our viewers who want to dig deeper into the topic, we highly recommend Dave's new book, Implementing Full Duplexing for 5G, published by Artech House. You can find it at their website, artechhouse.com.